Good morning, everyone, or afternoon, or whatever it is you happen to be watching this. Hope you all had a fantastic first day back. We're going to get straight into second derivative testing here. This is using the second derivative, and obviously we know that the second derivative deals with concavity, right? So it says, suppose f of x is continuous on an open interval that contains c. So it's continuous, means it's going to be probably differentiable. Obviously it's the second derivative here. If the first derivative is 0 and the second derivative at that same value, see this is c here? If the second derivative at that value is greater than 0, meaning positive, right? This is positive, then it has a local minimum because it's concave up, right? CCU, concave up. And if the first derivative is 0, meaning its critical value, right? And the second derivative is less than 0, so negative is, if the second derivative is negative, then it's concave down, frowny face. And it has a local maximum. So if it's concave up, it obviously has a minimum. If it's concave down, it's obviously going to have a maximum. And that's the second derivative test. You take the second derivative, use the critical values, which is where your first derivative is 0, use the critical values and do a concavity test. So it's a pretty easy process once you get into it. Critical values are given for f of x are x equals -1, 0, and 1. So these are the critical values. This is the first derivative set to 0 gives you these x values. Given the second derivative is, oh, they've already done the hard part for us. They've got the second derivative here. 4 minus 12x squared. Determine if any critical values are local extrema. So this is relatively straightforward. All I'm going to do is plug in this value into my second derivative. This is where the first derivative is 0. Where the first derivative is 0, I'm going to plug it in and see if it's positive or negative. So going into the second derivative here, 4 minus 12 times, let's do -1 first, -1 squared, and that's going to be what, -8? 4 minus 12, which is 8, -8. Alright, therefore, since this is negative, it's basically like doing a sign analysis. Since this is negative, it means that it's going to be here, concave down. So what this negative means, that means we have a local maximum. Local max at x equals -1. Let's do it for the second critical value. Remember, these critical values came from setting the first derivative to 0. So at the second critical value here, 4 minus 12 times 0 squared, which is going to give you 4. Is that positive or negative? Well, it's positive. So therefore we have a local max at x equals 0. And last one here, minus 12 times 1 squared. And again, that's going to give you a -8. Therefore we have a, ooh, wow, I wrote maximum and I meant minimum up here. Glad I caught that. This was positive, meaning concave up, which means it has a minimum. I'm sorry about that. I should have caught that. This is a local max down here at x equals 1. Okay, so again, the first derivative test, let's think about this. If this is what your function looks like, right? And let's call this -1 and call this 1. If this is what your function looks like, then at -1 and 1, your first derivative is going to be 0. The slope is 0 at a maximum or minimum. The second derivative test is how you tell if it's a maximum or minimum. So if it's concave down, like this part is, if the second derivative is negative, then it's a maximum. If the second derivative is positive, concave up, then it's going to be a minimum. Okay? Alright, So let's try this one more time here. Critical values given are -2 and 2. Given the second derivative is this. Determine if any critical values are local extrema. So even the second derivative is this. So we've got f double prime, I need to mark that as double prime, f double prime of -2. And I'm just going to plug in a -2 here. -2 squared minus 4. -2 squared. Just 4 minus 4 is 0 over 4, which is 0. Ooh. Now this is the second derivative test. Is this positive or negative? Well, it's neither, right? 0 is neither positive nor negative, so you can't tell concavity when you get a 0. So what we're going to say then is that we don't know. I mean, we're going to say it with mathy terms, but that's basically what it boils down to. So here's what I'm going to say. What I'm going to say is cannot determine using second derivative test if it's a local extrema. So I don't know. I cannot use the second derivative test to tell if it's a local extrema because the second derivative test is not positive or negative. It's 0, so it's not going to be concave up or concave down. Yikes! Now, when this would happen, an example of when this might happen is if you have a not a maximum or a minimum value, but a point of inflection, for example. That's when this would come about. If you have a point where it changes concavity, in other words, if it goes from something like this, see, that's still a critical value. It'll still be a horizontal tangent here when it changes from one to another. Another one is vertical tangents. Anything along those lines could be done somewhat like that. Anything along the lines of going to give you any type of asymptote, any spot where it might be undefined, anything like that. Now that's only one of them. We've only tested -2. So now let's test +2 very quickly. 2 squared minus 4 over 2, and again you get 0 over 4, which is 0. So again, you cannot use the second derivative test here. So to use the second derivative test, it has to come up being either positive or negative. That's all the second derivative test does. It's like the first derivative test will tell you if it's increasing or decreasing by looking at the sign. The second derivative test tells you whether it's concave up or concave down by looking at the sign. Okay, let's go to the back here. Zoom in. Even functions, if you will remember, for even functions, those are going to be functions that are symmetric to the y-axis. They also usually have even powers on them, like x squared, x to the 4th, x to the 6th. But they're symmetric to the y-axis. So what I would say here is, let's do this. Let's say it comes up like this. It is a function, so let's make it a little neat here. And then let's say it does the same thing over here. Now if this were perfect, this would be symmetrical to the y-axis. Alright, so let's look at concavity. Concavity for each piece of this function. So I'm going to look at the right hand side here. This is concave down, moving into concave up. So concave down, moving into concave up. Going the other direction, it's concave down, moving into concave up. So if you notice here, your concavity is the same. Talking about, either side of the function, the concavity is the same. So it's a mirror image of itself, right? It's taken from here and flipped over here. So your concavity is going to be the same. But your increasing decreasing is going to be opposite. Now here's what this is going to look like. If you notice here, this piece is concave down, this piece is concave down, this piece is concave up, this piece is concave up. So it's the concavity is symmetrical as well. But increasing, decreasing, this piece here is decreasing, and then it starts increasing here, and then it starts decreasing here, and then it starts increasing here. So your increasing is going to be opposites when you're talking about the right and the left. Starting from 0, you start with decreasing to the right, then go to increasing. Starting at 0, going to the left, you start increasing, then you get to your decreasing bit. So these are opposites. And you're going to see where this is going to be useful here in just a second. Odd functions look something like this. These are your origin symmetries. Remember, they're symmetric to the origin. So concavity, this is concave up, this is concave down. You can make this a little bit more drastic if you would like, so you can actually see the concavity here. I kind of drew it a little bit more straight than I should have, I guess. So concavity, starting to the right, you're up, to the left, you're down. So concavity is opposite. And increasing, decreasing. This is increasing here. Increasing here. So increasing, decreasing are the same. Now this is something that's going to be useful to us when we get down to something like this, where we're giving characteristics of a function. We have to fill in the rest. So it says, given f of x is odd, complete the table. So it's odd. It's one of these guys. So it's going to be symmetric to the origin. Now what that means is if I have a point kind of like 1, 2, 1, 2, then my next one is going to be -1, -2. Remember, origin symmetries mean that you change the sign of x and y. So -1, -2, right? 1, 0 is 1, 0. There's nothing to change there. Okay. On and on and on. Let me find the other numbers here. 2, 0, -2, 0, same old, same old. All right. Oh, I'm sorry. I should have put a 0 here. Now, that's just the base of the function, right? Just the basic function, this first line here. So, let's think about this here. For f of x, if you're going positive to the right, kind of like this one is, and its a symmetry to the origin, if you're positive to the right, then you'll be negative to the left. So this piece will be negative. See, between 0 and 1 it was positive, so between 0 and -1 it'll be negative. Then it goes to positive between 1 and 2, so here it'll be negative. Negative when it's greater than 2, so it's going to be positive over here. So the function itself, this is the origin symmetry. That's all the first line deals with. The origin symmetry. The first derivative tells with increasing, decreasing, and these are the same. See this here, increasing, decreasing. This is your first derivative. So this one's easy. All I got to do is look at this. It's positive here, it's going to be positive here. 0 here, 0 here. Negative here, negative here, negative here. And then the second derivative, concavity for odd, is opposite. So 0 here, negative here, which is positive here. It's opposite. Negative, 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 negative. So these are all going to be positive, 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 positive. Let's go down here. Odd functions. Now odd functions are symmetrical across the origin. Right? So here's the origin, right here, at 0. That means that with the symmetry thing, it's going to be the same on f of x. So very easily, here, negative, 0, positive, 3, positive, negative. Increasing, decreasing are opposites. So this is positive. See how this is negative, negative, negative? That means it's going to be positive, positive, positive. Increasing, decreasing comes from the first derivative, so they're opposites. 0, there is no opposite of 0, obviously. Negative and negative. Concavity is the same. Positive, 0, and the rest are negative. So just a little bit about the second derivative test here. It's really useful when it comes to graphing equations because you can look at something kind of like just an equation. You can do a second derivative test and you can automatically tell where it's going to be concave up or concave down. You can tell whether you're going to have a maximum or a minimum or neither, which we'll discuss some more of the neither stuff a little bit more in class. All right? So, second derivative test. Have a great one.